Good morning. It's my pleasure to introduce the final plenary speaker, Professor Jun He from Princeton University. Professor He took his PhD from Michigan under the direction of Mirza Mustada. He is renowned for his contributions between the interface between algebraic geometry, most particularly Hodge theory, and combinatorics. He has been a Sloan Fellow, time at the Institute of Advanced Study, Stanford, before he came to Princeton. He has received many honors. He was a plenary speaker, an invited speaker at the Rio ICM. He was the recipient of the New Horizons Prize from Breakthrough Prize Foundation in 2019. He was a Samson Ho-Am Prize winner, a Simons Investigator, the recipient of the 2022 Fields Medal, MacArthur Fellow in 2022, an honorary member of the Korean National Academy of Sciences, and most recently, a plenary speaker here. So let's give him a warm welcome.
Okay, thank you for the invitation and thanks for being here. I'm going to tell you about my recent joint work with Daoji Huang, Mateusz Mihalek, Botong Wang, and Shuda Wang. And it is about realization problems. And it is a very general type of problem, and today I'm going to tell you two flavors of it. One in convex geometry, and one in algebraic geometry. The one in convex geometry concerning projections of convex bodies is very, very intuitive, elementary, and I hope that everybody can appreciate the subtleties and beauties of it. I understand that I'm addressing a very general audience, and not everyone will be already familiar with the terms that I'll sometimes use in algebraic geometry, but nevertheless, I'm going to present in parallel the realization problems in algebraic geometry because together, the similarities between apparently unrelated two realization problems make it much more fascinating. But the kind of the algebraic geometry problems that I'm going to show you is rather elementary. So if you just pretend that you already know everything about algebraic varieties and so on, then I expect that you can get most of the interesting parts of the points that I'm going to make. At least I'll do my best to make that happen. Okay. So this is one of the most basic versions of realization problems that you can ask in the setting of convex geometry. Let's say you have a convex body, a compact convex set inside R4. And then you look at the 6 coordinate projections, pi ij, from R4 to R2. There will be 6 because you can project onto 1-2 plane, 1-3 plane, 1-4 plane, 2-3 plane, 2-4 plane, or 3-4 plane. And for each one of them, if you look at the image or the shadow of your convex body A, you'll get a planar convex shape, and you can measure the area of this planar region, getting a number for each one of the 6 projections. Let me call them P12, P13, P14, P23, P24, and P34. And the question is, which 6 numbers arise this way? If somebody gives you 6 tuple of non-negative real numbers, can you say whether there is or there is not a convex body A in R4 with those 6 projection areas? That's the realization problem that I want to address in the setting of convex geometry. So for example, If you start with a unit ball in R4, then the 6 planar projections will produce unit disk, 6 of them. And each one of them has area pi, so the number you get is pi, 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 pi. You get more interesting vectors by looking at polytopes, for example, the convex hull of E1, E2, E3, E4, E1 plus E2, and E3 plus E4. If you think about it, then almost all the projections are identical except the 2 special ones where you project onto 1, 2 plane and 3, 4 plane. And then these 2 last vectors will produce point 1, 1, and then your image will become a square rather than a triangle. So in this case, the vector in question will be 2, 1, 1, 1, 1, 2, if you pretend that triangle has area 1 and square has area 2. Everything I'm going to say, most of it at least, will be invariant under scaling of the vectors, so we can ignore the 1/2 part for now. Okay, the second question is in the setting of algebraic geometry. So for simplicity, let's work over algebraic geometry over the complex numbers. And one of the most simple algebraic variety over complex number is P1 over C. This is complex projective line, homomorphic to S2. Take 4 of them, take the product of them, and inside that algebraic fourfold, P1 to the 4, let's look at some surfaces in it. Irreducible surfaces in the sense of algebraic geometry. These are 2-dimensional complex algebraic varieties that can be defined by polynomial equations. In this case, essentially polynomial equations in 4 variables. Take any such thing as, and look at the coordinate projections, 6 of them, onto P1 to the 2, very much like as in the previous slide. And for each such projection, I'm going to restrict it to S, the surface, and in that way, S will cover the target P1 to the 2, generically, a certain finite number of times. It will be generically a covering map from S to P1 to the 2, although there may be some singularities. For us, we'll be just interested in how many times the surface covers the target P1 to the 2, and let's just call this number Pij. Again, I have 6 numbers, and I can ask the question, which 6 numbers arise this way? And one of the main results that I'm going to show you today is the complete answer to the first question. But you may be surprised to know that algebraic geometers, with all their fancy tools, we do not still have a way to answer the second question. So the second question, as far as I know, is still open. But I will going to show you some partial results and maybe suggest the general form of the possible answer. But let me just quickly point out that in the first version of the problem, the assumption that A is convex is absolutely crucial. So if you drop the assumption that A is convex, then the answer to the realization problem is trivial. If somebody gives you any 6 tuple of non-negative numbers, you can find the suitable A that hits those 6 numbers, because I can just put some pieces of A here, here in right directions to make it realize the 6 numbers. And if somebody wants your A to be connected, that's no problem at all. You just use a very thin string to connect the various pieces, and your A will do. So all the subtleties in the question 1 lies in the assumption that A is convex. And similarly, in the second version of the problem, the assumption that S is an irreducible surface is absolutely crucial. If otherwise, the answer is simply all 6 tuples of non-negative integers by just taking unions of suitable surfaces. Now I'm going to formulate the answer to the question 1. And here the realization problem is so simple, so in a sense this funky thing that I'm going to show you is not absolutely necessary in the technical sense, but it is very, very fun. So let me phrase the answer in this way. So there is something called T1 that Viro introduced in the context of tropical geometry a long time ago. I'm not going to tell you what a hyperfield is, but let me just simply say that it was originally defined as a field-like object where you can multiply two things and you can add two things, but the addition of two elements is not necessarily an element, but a subset of elements of the ground set. And it's subject to various axioms that I'm not going to show you. But it is the unique quotient of C under the absolute value map in the following sense. So the idea, I think, in retrospect, is to focus on the additive relations. So we are very used to think about algebraic objects as like a collection of binary operations. If you add two things, you get one thing. And you can multiply two things, you get one thing. And starting from these two, you can build the whole large world of algebraic geometry. But if you have ever done algebraic geometry, you will notice that algebraic geometers rarely add two things. The only thing that they care about when the sum of many things is equal to 0, because that is what defines algebraic geometric objects, the algebraic varieties. So instead of, let's just give up the idea that field is something that you add two things and you get the element. But just keep the relations. When is A plus B plus C equals 0? And then there is something called tract, which remembers exactly this relation. So it's a set where you can multiply two things in a reasonable way, and then you remember a ternary relation, which you formally write A plus B plus C equals 0. So collection of all A, B, C's that you declare to be added up to 0. And in the case of fields, you realize that this ternary relation completely determines the structure of the field. If you know which A, B, C add to 0, you know what the field is. But here, you can do much more generally. And for example, in this triangular hyperfield T1, you declare a ternary relation, A plus B plus C equals 0, exactly when there is a triangle with side lengths A and B and C. So it's a triangle inequality. That's the ternary relation. And the absolute value map from C to the non-negative real numbers is a homomorphism of this structure called tracts, in the sense that it preserves the multiplication, the obvious multiplication, and also it preserves the obvious ternary relation. The question here is, if you know that three complex numbers add up to 0, what do you know about the sum of their absolute values? The answer is exactly that you know that they must satisfy the triangular inequalities and nothing more. That's the meaning of this sentence. And now there's recent developments putting a framework how to think about these objects in the right way, introducing the objects called pastures and tracts and so on. What is interesting about this triangular hyperfield is that they come in families in the most obvious way. So for positive P, let's look at the pth power map of non-negative real numbers. So I have a T1, and that I want to introduce TP on the same ground set of non-negative real numbers, where I put the structure of a tract simply by saying that the pth power map is an isomorphism of structures. So in the target, I would say that A plus B plus C is 0 if and only if there is a triangle with side lengths A to the 1 over P b to the 1 over p, and c to the 1 over p. And it's an isomorphism. It's exactly the identical object. Why would you do something like this? Because the limit of all such things as p approaches 0 is a very interesting tract. And you can try to formulate a precise statement that I would express limit of p goes to 0 of Tp is equal to T0. T0 is a particular tract that people call tropical hyperfield, where the ternary relation is given by saying that A plus B plus C is 0 if and only if the maximum among the A and B and C is achieved at least twice. This structure is the basis of the field of tropical geometry. And in very precise sense, T0 is limit of Tp as p goes to 0. And this is a very concrete calculus statement, if you think about it. Okay, but today for us, we don't need a formal definition of a tract. We only need to know the definition of Grassmannian over this particular tract Tp. And for this, you don't need to know what a Grassmannian is, but it's a set of subspaces of, say, for example, over field. And you don't need to know what a tract is, because the whole thing, Grassmannian 2,4 over Tp, can be described very, very explicitly. And I'll tell you what it is. It's a subset. It's a closed subset of R to the 6 with coordinates p12 up to p34, each one of them being non-negative, such that there is a triangle with side lengths p12 times p34 1 over p, p13 times p24 over 1 over p, p14 times p23 over 1 over p. Everything considered modulo scaling, global constant positive number. And if you already know a little bit about Grassmannian of 2,4 as an algebraic variety, you will know that this set of all subspaces, the simplest kind of moduli space in algebraic geometry, is defined by a beautiful equation called Plücker relations. It looks exactly like that, but interpreted over a field. P12, P34 plus, no, minus P13, P24 plus P14, P23 is equal to 0. I'm just interpreting exactly the same equation, but over a more general algebraic structure that I term Tp. And it's exactly the Plücker relation. This set, you can already investigate with having a lot of fun, discovering a lot of non-trivial facts. The first fact is that this set is homeomorphic to 5-dimensional compact ball. I didn't tell you explicitly, but by a triangle, I mean I include degenerate triangle. For example, the flat ones like side lengths 1 and 1 and 2. So the result is this Grassmannian 2,4 is a closed set. And modulo I'll positive this is a compact set. And the claim is that this is 5-dimensional ball. This is not a trivial assertion, because you will see that the defining condition is not convex. If you have 2 points on Grassmannian 2,4 over Tp and add them, it's no longer, it need not be in Grassmannian 2,4 over Tp. So the assertion that this is homeomorphic to be 5 is non-trivial. So in particular, its boundary is S4. This is a non-convex compact ball in R to the 4 choose 2 modulo positive. And here's the answer to the first question. This is a solution to the realization problem. There is a convex body, A inside R4, with given projection areas, Pij, if and only if Pij is a point in Grassmannian 2,4 over T2. So if somebody gives you 6 numbers, you can immediately tell whether there is or there is not such a convex body A. What do? You multiply P12 with P34, that's one number. You multiply P13 with P24, that's second number. You multiply P14 with P23, that's the third number. For each one of them, you take square root and see if triangular inequalities are satisfied or not. That's the answer. So this is an if and only if statement. So, and both directions are non-trivial. So one direction that the necessity of Grassmannian 2-4 condition follows from my point of view, the Hodge index theorem. You can also deduce this fact from the Alexandrov's approach to Alexandrov-Fenchel theorem in convex geometry. The other direction is an explicit construction. Somebody gives you Pij, you want to construct A. And this is, in my opinion, a very interesting construction. I'll try to convince you that this is an interesting problem and with an interesting solution in the upcoming talks. But what happened to us was that we figured out that when given Pij is in the interior of this 5-dimensional ball, GR24T2, there is an obvious solution. And I'm going to show you what the obvious solution is. And then we notice that if my point Pij is on the boundary of this 5-dimensional ball, it's not so clear what we should do. But this, especially if somebody gives you a very concrete point on the boundary, for example, 3, 2, 1, 1, 2, 3, it's a very, very, very concrete problem. Is there a 4-dimensional convex body where projection areas are 3, 2, 1, 1, 2, 3? And initially, we had no idea. And we thought that this was a completely fair question for any bright-minded high school students or ChatGPT or Gemini or anything like that. And we were surprised to discover that, at least so far in my attempts, either bright-minded young people or ChatGPT and its variants have come nowhere close to the solution that we eventually found. But if you want to kill some time, this is a problem that you can think about starting right now. What is the convex body A with 3, 2, 1, 1, 2, 3? Okay, so let me now slowly start to tell you what the obvious solution is. So for that, I think it's instructive to try the easier version of the same problem. This time, let me look at the projections from R3 to R2. This is a very, very easy problem. And there will be 3 projections. And for each one of them, I have a projection area, Pi. And the question is, given non-negative P1, P2, P3, how do we find A? And in this case, there's no restriction on Pi's. No matter which Pi, you will always find A. And any reasonable person will say that, aha, there is an obvious solution, which is to look at the cube. And what should be the length of the cube? The length should be, obviously, P1 to the inverse, P2 to the inverse, P3 to the inverse, so that the projection areas will be P2 inverse times P3 inverse, and so on. But you can scale everything, maybe scale by square root of P1, P2, P3. And then if you do that, you notice that you'll get exactly hit the solution P1, P2, P3. And this is the obvious solution. And you think, okay, I'm done, but you're not, because you did not solve the problem in the boundary case when one of the Pi is equal to 0. This solution, you see, does not extend to the boundary. This is a divergent solution. And you will see very similar things happen for R4 to the R2. Okay, so this is what I believe. And there's no reason that I should be right, but there are some circumstantial evidences to indicate that this should be the picture. So conjectural trichotomy that I believe is that if you pose this type of realization problem for codimension 1 projections from Rn to Rn-1, the result is easy. It's basically the previous slide. And if you pose this question more generally for codimension 2 projections, pi ij, and we have shown you the answer for when the n is equal to 4, I believe that this is an understandable problem with beautiful answers. I only know how to solve this when n is 4, but I'll show you what should be in general true for general n later. The third thing that I believe is that if you ask the same question for codimension 3 projections from Rn to Rn minus 3, so somebody gives you n choose 3 tuple of non-negative numbers and asks you what is the condition for the realizability, I believe that this is an impossible problem, meaning that nobody will ever come up with a reasonable answer with the correct interpretation of reasonable, like as explicit as the ones that's given. But I may be wrong. Okay, so this slide is the one that belongs to algebraic geometry. And for this, all you need to know is that the complex algebraic variety, let's say smooth ones, you can consider as a real manifold, and you can look at the homology and cohomology of it. And whenever you have a subvariety of such a thing, it has a fundamental class defining a homology class. Okay, where your variety means reduced and irreducible scheme. You say that the integral homology class is realizable over Z if there is a subvariety with that homology class. So this is an algebraic analog of what topologists sometimes call Steenrode's problem. I mean, which homology classes are classes of submanifolds? Here I'm just asking it for subvariety. If you have a rational homology class, then I'm going to say that that's realizable over Q if some rational multiple of that class is realizable over Z in the sense of the first item, if there is a subvariety. And lastly, if we're looking at real homology classes, I'm going to say that that's realizable over R if it is a limit of classes realizable over Q. So this is the terms that I'm going to use. And you notice that the second question that I posed for P1 to the 4 is equivalent to the question of which homology classes in P1 to the 4 are realizable over Z. Because if you have a surface and if you know the degree of the 6 covering maps to P1 to the 2, that is exactly the information of the homology class of S inside P1 to the 4. The homology class remembers exactly those 6 numbers. And you can identify the 2 vectors using the Kunetz decomposition in the obvious way. And the theorem that you can prove is that middle homology class Pij is realizable over Q, meaning that some multiple is a class of a reduced and irreducible surface in it, if and only if Pij is a point in the Grassmannian 2,4 T2. So very similar to the convex geometry problem that we've seen. For algebraic geometers, it's rather interesting to compare the first statement with the second statement, which says that Pij is a complete intersection class over Q, meaning that some rational multiple is a class of a complete intersection, if and only if Pij belongs to the point in the Grassmannian 2,4 over T1. Here I'm looking at triangular inequalities after taking square roots of products of Plücker coordinates. Here I am not taking square root. And complete intersection are those surfaces that can be defined by 2 polynomial equations in P1 to the 4. So most people who are not algebraic geometers will think that if you have a codimension 2 geometric object in a 4-dimensional space, it's very natural to assume that this is defined by 2 equations. But algebraic geometers have known for a long time that many of the codimension 2 objects cannot be defined by 2 equations only. And these are what complete intersections are. And you see that even their homology classes are rather different. Okay, let's practice some explicit examples. Suppose Pij is all ones vector, then this is a point in Grassmannian 2,4 over Tp for basically any p, because there is a triangle with 1, 1, 1. And it is not hard to see, if you have a trained eye, to see that this class is the class of an irreducible surface in P1 to the 4, but it cannot be a complete intersection over Z. On the other hand, 2, 2, 2, 2, 2, 2 is a complete intersection, class over Z. So here you see the subtleties that involve the multiples. More interesting example is 1, 1, 1, 1, 1, 3. This is a point in Grassmannian 2,4 over T2 because there is a triangle with side lengths 1, 1, square root 3. So according to the theorem, this class is realizable over Q. But it turns out that there is no surface with homology class 1, 1, 1, 1, 1, 3. It just so happens that 2, 2, 2, 2, 2, 6 is the class of a surface inside P1 to the 4. Okay. So this is the reason why I know 1, 1, 1, 1, 1, 3 cannot be realizable over Z. Because if there is a surface with that homology class, then I know the following inhomogeneous inequality must be true. P34 is at most P13 times P24 plus P14 times P23. This is violated by 1, 1, 1, 1, 1, 3. 3 is larger than 1 plus 1. And the proof is not difficult. You just look at the pi 3 and pi 4, two projections, and just apply this universal fact that a set is contained in the inverse image of its image under any map. So you just apply that thing and translates to that one. And the conjecture, which I believe will be the answer to the question 2, is the Grassmannian 2,4T2 condition together with this inhomogeneous inequality will characterize the homology classes of irreducible surfaces in P1 to the 4. At least on the interior of Grassmannian 2,4T2. So generically, this will be the answer. Here, I will have to put a little check here because I need to work affinely. So without this check, I usually work with everything modulo up to a multiple. But this realization problem over Z, I cannot work up to a multiple. And that's the whole point. Okay, so how do I know that 222, 226 is the class of a surface? So the real theorem you prove here is the following finer statement. Suppose you have an integral 6-tuple Pij that satisfies the T2 triangle condition. If Pij are coprime integers and L is any prime number, then either Pij is realizable over Z or L times that homology class is realizable over Z. So if you know that 1, 1, 1, 1, 1, 3 is not realizable over Z, then you know that 2, 2, 2, 2, 2, 6 is realizable over Z, and 3, 3, 3, 3, 3, and so on. The thing that's interesting about the proof of this statement is that the proof is transcendental. It uses a rather delicate complex analysis encoded in what geometers call the global Torelli theorem for K3 surfaces. But this is just one construction, so there may be another way of doing this. And the proof is to construct a suitable K3 surface, and algebraic geometers know a lot about them, and you put those surfaces inside P1 to the 4 to hit the given integral vector. And the conjecture for geometers or algebraists will be that the same exact statement will be true in characteristic P as well. So we do not currently know how to prove that. Okay. So now let me go to n dimensions and try to formulate the realization problem in n dimensions. And in particular, I'm going to give you the promised conjecture that which n choose 2 tuples of non-negative real numbers will be the projection volumes of an n-dimensional convex body. And for that, I need to remember this definition, which appeared in Federico's talk today morning. I'm going to say that n by n symmetric matrix Pij is Lorentzian if every Pij is non-negative and the matrix has at most one positive eigenvalue. And when the matrix is 4 by 4, this condition has mysterious relationship, but actually a very elementary one, to Grassmannian 2,4 over T2. So I'm going to show you that lemma, which I discovered in collaboration with another group of people, Matt Baker, Oliver Lorscheid, and Mario Kummer. And I want to take time to introduce this lemma because the lemma is very, very explainable. It's a linear algebra, and it's very, very cute. And this is my chance to follow the unique tradition among mathematicians as opposed to other types of scientists and academics, is to try to relate their newest discoveries to the works of all these people that they can ever locate. And this is our record so far. So the lemma we have discovered is this, and we have noticed that if you are generous in interpreting the works of the masters, then you can say that Cayley already knew this statement, or even Heron of Alexandria knew this. So that's some Greek person that lived more than 2,000 years ago. And the statement is the following. Suppose you have 6 numbers Pij, and the condition that that vector belongs to Grassmannian 2,4 over T2 is equivalent to the statement that 4 by 4 matrix with 0 on the diagonal is a Lorentzian matrix. And Heron must have knew this because he's the guy who figured out the formula of the area of the triangle in terms of its 3 side lengths A, B, C. And there is an expression which is that the area is square root of some polynomial in A and B and C. But he must have known that he cannot take the square root of negative number, right? So the thing that he's taking square root of must be non-negative, and he must have known this, presumably. And that is equivalent to this. So let me show you what happens if you try to justify this. I think basically everyone will arrive at the same proof, and it's based on a little miracle. So if you want to check that some matrix is Lorentzian, the main thing is to check that it has at most one positive eigenvalue. And for that, for 4 by 4 matrix, there is really only one thing you need to check, namely the sign of the determinant. Because 3 by 3 matrices with 0 on the diagonal, they already have a fixed sign of the determinant. So you try to decide the sign of the determinant of such symmetric 4 by 4 matrix. And then you quickly realize that if you expand the determinant, it's a some degree 4 polynomial, then it's an irreducible polynomial. But that does not mean that you cannot factor it. You can factor it, and in a very beautiful way. And here's the factorization. And this irreducible polynomial is a product of 4 things, and these 4 very nice things. And you see that this is essentially what shows up inside the square root of Heron. And the factors have the property that the sum of any 2 such things has a fixed sign. So saying that this determinant is non-positive is same as saying that every vector has a fixed sign, which is equivalent to the 3 triangle inequalities that defines Grassmannian 2,4 over T2. You see one triangle inequality here, another one, and another one there. So that's the proof. Okay, so having this lemma in mind, let me try to extend the algebraic geometry realization problem to n dimensions. Suppose you have a product of n projective spaces, maybe P1, 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 but really anything, P2, P3, P5, P13, or P, many of them. And consider the pullback of the ith hyperplane class to the product, Hi. And whenever I made the mistake of not replacing this CH, but pretend that this is a homology group. This is a Chow group, that algebraic geometer's version of homology. I just wrote it there that the statement works over any field. So if you have a 2-dimensional homology class, you can produce a number, Pij, by intersecting your surface class with pullback of hyperplane from ith vector and pullback of hyperplane from jth vector. This is an integer. And you can do this for any I and any j, so resulting in a matrix Pij. And the theorem is that this homology class is realizable over Q if and only if this intersection matrix is Lorentzian. This extends what happened for n equals 4. Okay. And this is the corresponding conjecture in convex geometry. Suppose you have Rn, look at n choose 2 projections pi ij, and then the prediction is that there is a convex body A with projection volumes Pij if and only if the matrix Pij is Lorentzian, where the diagonal is 0. Okay. So I can take one of the many directions from here, but I want to spend my remaining time in trying to show you one direction, namely that if somebody gives you 6 numbers, how to find the convex body A. I mean, of course, the answer is not unique. And the solution space, I think, has very, very interesting geometry. So given Pij, what can you say about the space of all convex bodies with those projection areas? Because this, I don't know how much convex geometers have went into this direction, but the same problem in algebraic geometry is one of algebraic geometers' favorite type of question. If somebody gives you a homology class, first question would be, is there a subvariety with that homology class? But the more refined question is, what is the shape of the space of all subvarieties with that given homology class? This is the topic of Chow varieties and other kinds of related moduli spaces. And oftentimes they have a very deep and mysterious geometry. I'm just pointing out that you can ask the same question in the setting of convex geometry. So now for n equals 4, I'll tell you that at least there is an obvious solution. I'm not claiming that the obvious solution is the only solution, but there is a canonical way of constructing A. Of course, this is not a well-defined formulation. Different people may arrive at a different answer, perhaps, but I think any person with keen interest to the symmetry of the problem will basically arrive at this solution, which I'm going to show you. And it has that same key property, namely that it's a divergent solution. The solution makes perfect sense. Everything works beautifully in the interior of Grassmannian 242, but the solution does not extend to the boundary. For the boundary, you have to do something else. We don't know why that happens. I mean, there are solutions you can artificially make up to extend the solution to the boundary, but I think in order to do this, you have to break some interesting symmetries. So let's start from Minkowski's fundamental observation more than 100 years ago. This is a beautiful observation. So suppose you have n convex bodies in R to the d, and let's consider the function that measures the variation of the volumes of Minkowski sums of the convex bodies AI. His observation is that this function is in fact a degree d homogeneous polynomial in the variables xi. And in fact, the coefficients of this homogeneous polynomial are what they call the mixed volumes of convex bodies. And trying to understand the possible inequalities between these mixed volumes of convex bodies is the main subject of the so-called Brun-Minkowski theory. So it's exactly our kind of problem. It's a realization problem. We will mostly need this theory only in the plane, where we can picture everything. So here, consider the case when you have two convex bodies. One is a polygon and the other is a unit disk. And the polynomial that we want to understand is that the one that measures the variation of area when you add A and B, or some multiples of A and B. And that we can clearly picture in the following way. So if I have XA, which is the polygon, then adding the unit disk is like looking at the epsilon neighborhood of this polygon. And we can understand how the area varies. So there will be two components, which is the x squared term, the area of A, that's the main term. And then there will be the area of the B, y squared term, that measures the colored portion. And then there will be other part, these other parts. And you can clearly see that this other term will be proportional or exactly equal to the perimeter of A. So this is just a general observation. That's true for any A and B. And if you look at this homogeneous degree 2 polynomial and view it as a symmetric matrix, 2 by 2 matrix, by taking the Hessian of it, you notice that the Hessian is a Lorentzian matrix exactly when the determinant is non-positive. That is the determinant there, and the determinant turns out to be a very familiar thing. It says that the 4 pi times the area of A is at most the square of the perimeter of A. This is the very classical isoperimetric inequality of Minkowski. So you can see the very basic version of Lorentzian shadow in this setup. Okay. So let's give name to this mixed volume. So suppose I have convex bodies A and B in R2. The mixed volume, or mixed area in this case, of A and B, I'm going to write by mv of ma comma b. And it's simply the coefficient of xy in the polynomial area of xa plus yb. So when B is a disk, this is the perimeter of A. Okay. So now I'm ready to tell you the obvious construction of a 4-dimensional convex body with given 6 projection areas. And I want to show you some computations here to convey you the idea that this Grassmannian 2,4 over T2 is really a Grassmannian. So I didn't claim anything about it. So it's, geometers will think that it should be the set of subspaces of something, and what do you mean by a subspace over T2? And I haven't addressed any of these questions. I just took the equation, Plücker relation from algebraic geometers, and just plugged it in. But it has many of the formal properties that the more familiar Grassmannians have, And computations, hopefully, will convince you that it's a very, very similar object. So now let me show you the obvious construction. First, I'm going to focus on the symmetries of Grassmannian 2,4 over T2. There are two obvious groups that X on Grassmannian 2,4 over T2. One is the symmetry group of S4. S4 permutes the four elements in the obvious way. So Pij goes to P of a sigma I and sigma j. There's another much larger group that X on it, which is the R4 to the positive. So positive orthant of R4. So this sixth tuple of numbers, Pij, is secretly the wedge 2 of R4. That's why they are labeled by ij. So P12, P13, and so on, up to P34. And R4, the positive numbers, acts in the obvious way. So if somebody gives you lambda 1, lambda 2, lambda 3, lambda 4, it sends Pij to lambda I, lambda j, Pij. If you think that Pij is a symmetric matrix, as we have seen in the lemma, then this is simply scaling the matrix by row and column scaling simultaneously by lambda I. And you know that this does not change the signature of your matrix. So clearly it preserves the Lorentzian property. So clearly it preserves Grassmannian 2,4 over T2, which you can also check very directly. So let's keep this symmetry in mind. And then what you can realize is that you can put any vector, 6 vector, into a normal form using the scaling action. This is a little exercise in pre-calculus. And you notice that you can put this 6 vector in the normal form so that the first one is square root of P12, P34. Second is square root of P13, P24. Third is square root of P14, P23. And the other 3 is determined by the first 3. So there is a symmetry along this midline. So these 2 are the same, these 2 are the same, the outer 2 are the same. Well, why do you want to do this? It's a kind of linearization, because if you just look at points of Grassmannian 2,4 over T2, then the fact that UVWWVU is in there is simply the condition that there is a triangle U and V and W. So in a sense, I have eliminated square roots from the problem. It's a linearization. And you notice that I can take the normal form because the realization problem is also invariant under scaling of 4 things. So if you found the convex body A for the normalization, then you can recover A by simply scaling the 4 coordinates of R4 in which A lives in. So I'm going to just consider the vectors UVW, WVU. And here's the second definition. Suppose I have 2 convex bodies in R4. This is like a multi-linearization. So it's also a linearization. So A and B are convex bodies in R4. I'm going to formally introduce the symbol A wedge B. Pretend that A is a vector, although it's really a convex body. I want to take the wedge product of that. And by definition, it will be 6 tuple of numbers, or more precisely, element of lambda 2, R4, the second wedge of R4, where Cij is the mixed volume of pi ija and pi ijb, mixed areas of the projections. And using this notation, I didn't do anything, it's just a notation. We can restate our formulation problem as follows. Given Pij in the Grassmannian 2,4 over T2, solve the equation A wedge A is equal to Pij. It's exactly the same problem because the mixed volume of A with A is simply the volume of A. I want to put a little circle here just to emphasize that this obvious solution will only work in the interior of this 5-dimensional compact ball. Okay. Here are two very easy lemmas that you can immediately observe. A wedge B is equal to B wedge A, simply because mixed volumes have that property. Notice that there's no minus here, or there is a minus, but inside T2, 1 is equal to minus 1. The second easy lemma is that for any non-negative real number, lambda 1 and lambda 2, if you take the wedge of lambda 1A1 plus lambda 2A2 with B, then that's same as lambda 1 of A1 wedge B plus lambda 2 A2 wedge B. So the two plus signs obviously have very different meanings. The first plus is the Minkowski sum of convex bodies. The second plus is a sum of two 6 vectors. Again, you have this property because the mixed volumes have that property. So let's use these two lemmas. And this is where some aesthetics comes in. So Grassmannian 2,4, or whether second wedge of R4 has interesting symmetry other than S4. Namely, that there is an extra symmetry that sends 2 set inside the 4 set into its complement. So Grassmannian 2,4 is self-dual. There is an extra symmetry not coming from S4. That suggests to look at the following 3 line segments. The first connects E1 plus E2 to E3 plus E4, where EI is a standard basis vector. Second is E1 plus E3 to E2 plus E4. The third is E1 plus E4 to E2 plus E3. And it's easy to compute the 6 projections for each one of the line segments, and it looks like this. Well, now we compute the wedge products. Because the mixed area or mixed volume of this line and this line in the plane is 1, maybe it's 2, but it's not important for us. And the mixed volume of line segment with itself is 0. From this picture, we can compute all the wedge. P wedge Q is 1, 1, 0, 0, 1, 1. P wedge R is 1, 0, 1, 1, 0, 1. Q wedge R is 0, 1, 1, 1, 1, 0. This is an easy computation. Now let's use this thing to solve the equation A wedge A equal Pij, given Pij in GR24T2 interior. You need to focus on where I use the condition that Pij is Grassmannian 2,4 over T2. Because if you don't use this condition, you know for sure that there will be no such convex body A. Okay, first step is normalization. So suppose that Pij is already normalized. I'll just put some number 4 there to make the later formulas cute. We can do that. That's just group action on Grassmannian 2,4. The second, I'm going to make a guess. And this is what I mean by the obvious solution. So in the R3 to R2 case, the obvious solution was cube. I declare that in this case, the obvious solution will be the Minkowski sum of those 3 special line segments that remembers the very special symmetry of Grassmannian 2,4. So I don't know what my x, y, z will be, but just suppose that my A is a sum of xp plus yq plus zr. And then we compute using the previous slide. We know what p wedge q is, p wedge r is, q wedge r is. And if you use that, you arrive at this very explicit vector in terms of x and y and z. And now our problem can be restated as follows. If somebody gives you a non-degenerate triangle with side length u and v and w, can you find non-negative real numbers x and y and z such that xy plus xz is 2 times u, xy plus yz is 2 times v, and xz plus yz is 2 times w? I mean, again, it's a matter of opinion, but I think this is a very beautiful set of equations with right kind of symmetry between x, y, z, and u, v, w. So let's try to solve this and see what happens. First of all, I can add the 3 equations to get that xy plus xz plus yz is equal to u plus v plus w. And in turn, I can use that to get each one of the summands, namely xy must be u plus v minus w, xz is u minus v plus w, and yz is minus u plus v plus w. And the point here is that these 3 numbers are strictly positive, because that is my assumption that there is a triangle UVW. But because of the symmetry of the situation, I can take the product of 3 left-hand sides and 3 right-hand sides to determine what should be x, y, z. It is a square root of the product of 3 things on the right. And then I can plug that back in to get the final solution. The conclusion is that the system admits a unique positive solution, which is given by x equals square root of product of the 3 things that appear in the triangle inequality with 1 reciprocal among the vectors. And similarly for the other guys, where you take the reciprocal in different positions accordingly. And that is your A. You simply take the Minkowski sum of the 3 distinguished directions with the correct length. Okay. Again, let's notice that this is a divergent solution. Suppose, imagine your UVW, it's a triangle initially, but it limits to a degenerate triangle. Then one of these expressions, like u plus v minus w, will approach 0. And one of these quantities will contain that expression in the denominator. And that will going to blow up. And therefore, you don't know which A you should take on the boundary of Grassmannian to 4. So on the boundary, what we do is to construct a particular solution. It is a family of 4-dimensional polytopes with 16 vertices. Why 16? I mean, if you have been that killing time toy exercise that I suggested earlier, you may have been playing with polytopes with 4 vertices or 5 vertices or 6 vertices, but probably not 16. But the point here, rather amusing fact, is that it has to be 16. And how do I know that? Because if you know a little bit of Brun-Minkowski theory, this Lorentzian condition, which is necessary, you will notice that it really comes from the proof of Alexandrov-Fenchel inequality on mixed volumes. And there has been a long thread of works trying to characterize the equality cases of Alexandrov-Fenchel inequality. That is exactly the study of the boundary of Grassmannian 2,4 over T2. And if you're an expert, you may also know that there's a recent breakthrough on trying to understand the equality cases of Alexandrov-Fenchel inequality by Van Hendel and Schemfeld. And they give a very precise characterization of the kind of polytopes or more general convex bodies for which the equality cases do happen. And if you look at their if and only if characterization of equality in our setup, you know that you have to take 16 vertices, and it has to be 16 vertices in a very, very particular position. So that's the situation. So which I think it is fascinating to consider the similar problem in R5 and higher dimensions. So for example, in R5, you look at 10 coordinate projections to R3. Somebody gives you 10 numbers, and you want to know when you can find the convex body in R5 with given projection volumes. You have the conjectural characterization, namely that 5 by 5 matrix with Pij as entries has one positive eigenvalue. And your problem is to construct a 5-dimensional convex body if somebody gives you a 5 by 5 Lorentzian matrix. And clearly, the first step is to find the obvious solution in the interior, I think. And this is already an interesting problem. And I believe it will have a beautiful answer, but not a too obvious one to make it dull. So thanks for your attention. I'll stop here.
Thanks for the lovely talk. Are there questions?
I just wanted to confirm, so the solution that you created for the interior is unique, and for the boundary as well?
Unique given my ansatz, yeah.
Yeah, okay. And so, like in the boundary as well, it's a unique solution? Or like this family of polytopes?
Unique in a suitable sense. And in order to understand what I mean by that, you will have to read the paper.
Okay.
Yeah.
Other questions? Anyone? Okay.
Thanks. My question is about the Z realizability sequences that you have. So you seem to be freely scaling stuff.
When I'm asking Q realizability, yes.
Right. Does what you were saying that if something fails, then your infinitely many prime multiples of it will be realized, right?
Yes. Yes.
So does that mean that the Minkowski sum doesn't behave well under the Pij maps?
Oh, so I have only introduced this integral realizability problem in the context of algebraic geometry. But you can ask the same integrability realizability question in convex geometry.
Right.
So the question here would be, if somebody gives you, for example, a 4 by 4 Lorentzian matrix with integer entries, can you find the lattice polytope in R4 whose projection areas have the given Pij as volumes?
Right.
I do not know the answer. So over Z, I do not know answer in P1 to the 4. I do not know the answer for lattice polytopes in R4. But I expect their answers will look very similar. And I have briefly indicated what the answer should be in the algebraic geometry setting.
So the Pij doesn't behave well with Minkowski sums then? Like you can't add the projection maps? Or maybe I'll ask later.
You mentioned that if the dimension drops by 3 when you project, then you think is, how you say it, impossible to find a good answer. Can you maybe say something? What do you mean by impossible?
That's right. So it's just a belief. It's a belief. And what I can tell you is the reason why I believe that should be the case. So I don't think I have ever used the word matroid in this talk, but that is what I have in mind. And these very general types of Grassmannians you can think of as the set of matroids over T2, over field, over some more exotic structures, and so on. And for each one of them, you can pose the same kind of realizability questions in exactly the same way. And matroids are some type of incidence structures. And the incidence realization problems apparently tend to have the following property. If you ask the realization problem for rank 1 incidence geometries, it's trivial. If you ask the realization problem for rank 2 incidence geometries, it's not trivial, but quite easy and understandable. If you ask realization problems for rank 3 incidence geometries, it's impossible in very precise sense, depending on which context you're talking about. So this is the subject of universality theorems in realizability. So over Q, it says that matroid realization over Q is equivalent to Hilbert 10th problem over Q. And over R, it says that realization space over R can be basically homeomorphic to any reasonable space. Over C, it says that the realization space over C as an algebraic variety can arbitrarily complicate the singularities and can have arbitrary birational type, and so on. So depending on the context, what it means to be impossible varies, but strange force of nature tries to tell you that rank 3 problems are impossible. And my belief is that it should be also the case for T2. And if you consider convex bodies or algebraic varieties.
I have a question. Have you thought of symmetry? Like what type, for example, of centrally symmetric convex body have given?
Oh, that I don't know, but I expect it will be interesting. Yeah.
Well, let's thank the speaker again for a wonderful talk. The next talk will start shortly. Thank you.